What do you think of when you hear the word inference? I think of observing something and using that information to indirectly infer something about something that I didn't observe. See, inference is one of the most important concepts in all of probability, and it's all about using observed evidence to infer something about something you didn't observe. And it often involves testing hypotheses. So let's make a concrete example out of this. Let's say we observe a puddle on the ground. There are two hypotheses that could explain this. Either hypothesis one, it rained, or someone maybe, I don't know, was watering the grass, or they spilled a bucket and now there's water all over the ground. We observed the puddle, the evidence, but the cause of the puddle was unobserved. Was it hypothesis one or two? You see, inference is using the puddle to draw conclusions about whether or not it rained. But even though something can be unobserved, we usually still have a prior belief over what happened. I mean, we all have prior beliefs about the state of the world, right? And in this example, a prior could be that the Weather Channel forecasted like a 10% chance of rain. But as soon as we observe that puddle, we can infer that it probably did rain. And now our prior belief has been updated. So the most important thing to remember as we move forward is that inference is using new evidence to update our beliefs over what happened. Now, the king of inference, and arguably the most important equation in all of probability, is called Bayes' rule, and I'll write it out now. It says that the probability of event A occurring given event B occurred is equal to the probability that B occurred given A times the probability of A divided by the probability of B. Now, this is not intended to make sense right now, but we're going to walk through a concrete example and actually derive this equation, and you will understand it so much better. All right, so you see a puddle on the ground, and we want to know the probability that it rained given the ground is wet. And I'm going to stop saying puddle to avoid confusion with this P, and W will represent that the ground is wet. So this is what we're after. How can we express this in terms of things we know? Well, the easiest thing to do will be to start by just drawing it out. So this is the possibility space of every event where the ground is wet. This is the possibility space of every event where it rains. And this is where both happen. And I'm going to use that sort of upside down U as an and symbol. Well, we want to know the probability that it rains given the ground is wet. And whenever you hear given, you should think it's an assumption, and the possibility space collapses down to what we're given. So given it rained, we can really given that the ground is wet, we can completely ignore this possibility space. And we have this. And what's interesting is you'll note that what I've drawn here is just one piece of the pie. This is a part inside of a whole. And that's all a probability is. It's just one selection of events divided by all of the events that could happen. It's just a piece of the pie. So we can write the probability that it rains, given the ground is wet, as the probability that both happen divided by the probability that the ground is wet. Now, we can rewrite this to get an expression for the joint. And by joint, I mean just the probability that both occur. It rained and the ground is wet. And this will equal the conditional probability times the probability that the ground is wet. But a core principle of Bayes' rule that we'll learn is that this is also equal to the expression where you flip the R's and the W's. The probability that it's wet given it rained times the probability that it rained. Right? So both of these expressions just say the probability that both happened. This assumes that the ground is wet, but it just so happens that it also rained. Whereas this assumes that it rained, and it also just so happens that the ground is wet. So these two expressions mean the same thing, they're just coming from different perspectives based on what your assumption is. And what we're going to do is take this expression and plug it in for the joint. And what we now have is the probability that it rained given it's wet, which is what we're really after. All that is equal to is the probability that it's wet given it rained times the probability that it rained, and then we can't forget our denominator up here. So this is Bayes' rule, which we just derived. This term over here is the likelihood. It is the likelihood of observing our evidence that the ground is wet. Here's our prior belief, the probability that it rained. This would be the information that we get from the weather forecaster. And this term down here, this is a little tricky to understand. Actually, no, it's not. This is the marginal, and it's a normalizing constant. So let me ask you, what is the probability that the ground is wet? Now, we haven't actually put numbers to this, but how would you attempt finding this probability? Well, we could say that the probability that it's wet is the combination of the probability that it's wet and it didn't rain, plus the probability that it's wet and it did rain. All we're doing here is summing up all possibilities. So the probability that it's wet, like I said, is the probability that it's wet and it rained, plus the probability that it's wet and it did not rain. Now, we can use our identity up here and rewrite this in terms of a conditional probability. So our likelihood times our prior, and then our marginal is, let's see here, this is going to be the probability that it's wet given it rained times, the probability that it's wet given it rained times the probability that it rained. And this here is going to be the probability that it's wet given it did not rain, which I'm denoting here by a bar, times the probability that it didn't rain. So again, this is just a joint probability, and so is this. It's wet and it didn't rain. It's wet and it rained. And this is it's wet and it didn't rain. And now we've broken Bayes' rule down into something that we can actually compute. You'll normally see Bayes' rule written in this form, but it's always a good idea to break this marginal down into the sum of all possibilities. So let's actually put some numbers to this and work through an example. So you see that the ground is wet. Let's say earlier that morning, the weather forecaster told us that there's a 10% chance of rain. And just using common sense, we can say that the probability it's wet, given it did rain, is going to be really high. If it rains, you should expect to see wet ground. So let's set that to 95%. I think that seems reasonable. We'll also need to know the probability that the ground is wet, given it did not rain. And seeing as I don't see so many people on campus dumping water buckets over, I'd say that there's a pretty low probability of seeing a wet ground given it didn't rain. And the last bit of information we'll need is the probability that it did not rain. And what do you think this is going to be, given the information that we already have? Well, it can either rain or not rain. So there's a 100% chance of either one of those things happening. So the probability that it didn't rain is just 1 minus the probability that it did rain. Now, let's plug in some numbers, and I think we're going to find an interesting conclusion. So we see our puddle, and the probability that it rained, given our puddle, given that the ground is wet, let's see here, let's plug and chug. The probability that it's wet, given it rained, is going to be very high, 95%. And we'll multiply that by our prior belief, the 10% that we are given. Now, we're going to put the same numbers down here. Right? Because our numerator is present in our denominator. This is just a part over the whole, and that's all a probability is. Now, we need to have the probability that it's wet given it did not rain. That's going to be very low. Multiplied by the probability it did not rain. And that's going to be 1 minus 10%, which is 0.9. So, we get 0.095 divided by 0.095 plus 0.63. And I happen to have done this computation, and we get that there's a 60% chance that it rained given we saw the ground is wet. Now, I don't know about you, but this is a fascinating conclusion to me. Earlier this morning, the weather forecaster told us there's a 10% chance of rain. But as soon as we see that puddle, our prior belief totally changes. And now it's all of a sudden really likely that it did rain. Well, that's it. That's what I wanted to show you. I just think it's so cool that this math exists that lets us quantifiably assess the impact of new information. And I hope you'll remember what inference is moving forward, because you'll need it in any of your probability classes. Remember, when you're out in the real world and you see new information, you have to be open to your beliefs about the world changing. Till next time, I'm Graham.